Okay. So this is problem 33 from chapter 29. 33. So in this problem, we have two rails, two parallel rails, and resting on these two rails is a conducting rod, okay? And we have some magnetic field that's pointing towards us, uniform magnetic field, and this rail and the rods are perpendicular to the magnetic field. Okay? Right. So if the rails are horizontal and the rod is given an initial push, will the rod travel at constant speed even though a magnetic field is present? The answer is yes. Right? So these are, by the way, labeled A and B. So if we give this a little push, these are frictionless, so it moves freely on these rails. Even though there's a magnetic field present, if we give this a push, it's going to move freely because there's going to be no force acting on it. To have a force, for this magnetic field to cause a force, you need to have a current, and to have a current, you need to complete the circuit. Right? Here, these are disconnected for part A, so there is no circuit and there is no current passing through this rod, so there is no force, and it's just going to move with constant velocity. Now, for part B, suppose that t equals 0, when the rod has speed v is equal v naught. The two rails are connected electrically by a wire from point A to point B. Assuming that the rod has resistance R, and the rails have negligible resistance, determine the speed of the rod as a function of time. Discuss your answer. So v at t equals 0 is v naught, v0, and we are required to find how this is going to change. Now, this is going to slow down. It is going to slow down because now we connected these two. We are going to have some current passing through, and that current is going to lead to some force. Okay? So, are we given this? Well, anyway. So let's say that this distance is going to be some L. The force that's felt by this rod as a current passes through it is going to be B times I times L. Okay. So this current here is a result of the induced EMF in our circuit. So that current is going to be the induced EMF divided by the resistance of this rod. Remember, the rest of the rails has no resistance, so this is all the resistance we have. And this EMF is going to be just the induced EMF, so d phi beta by dt. Here our magnetic field is constant, so this is going to lead to some spanning of this magnetic field, and so the induced EMF is just going to be B times L times V. Okay, this just gives the rate of change of area, and this is just magnetic field, and so this is going to be the rate of change of magnetic flux. Now, if you plug this in and then divide this out, our force is going to be BLV divided by R times L. So this is B square L square V, or divided by R times V. Okay? Now this F is the mass times acceleration, so I can write this as mass times dV by dt, and now I can put all of this together. This dV by dt is going to be B square L square by m R times V. Okay? So in fact, this is the rate of decrease, so there is a negative sign in front. Okay? So this is how this force is in the opposite direction to the initial velocity. It's going to, of course, oppose the motion, and so there's going to be a negative sign. Now, this is a function of time, and when I take its derivative with respect to time, I get the function itself times some constant. Okay? So the only function that behaves this way is an exponential, so my v must be e to the minus a times t. Okay, where a is going to be some positive constant, so when I move it to the front, the negative sign is going to appear naturally. So if you take the derivative of this, dv by dt, this gives you minus a e to the minus a t, which is of course just v. Right? So now we can identify this a with this b squared L squared divided by m times r. So my V must be e to the minus v square s square over m r times t. Okay? So if you take the derivative of this, you get this differential equation over here. And in this case, the velocity is just going to decay exponentially, very, very rapidly. But note that if the resistance is very, very high, then this K constant is going to be very, very small, so it will take a very long time for this velocity to vanish. In the limit, R goes to infinity, we will have no current passing through the rod, so we recover the situation in part A. If there is no current, then you'll get constant velocity, whereas if this adds up to something large, then the decay is going to be very, very rapid. It just depends on how these are balanced. And I think that's all for this part.